Right, there's quite a bit to get through on this tutorial. So the last video we talk about the movement of water to the plant, but the focus really was just the roots. So this time we're going to do a quick recap of how water's moving through the roots. This is a picture of a root. Hopefully you're starting to recognize these drawings and you're doing them for yourself. You can see the little X, the xylem, and there's our little phloem there. This must be our vascular bundle. And this region going around it is the endodermis. And then this big region here is our parenchyma tissue, or the cortex. And then we go to the very edges where our root hair cells are. So we'll do a recap of how water gets from A to B to C to D, from the outside to the inside of the root hair cells, across to the other end of the cortex, where the endodermis is, and how it gets across the endodermis into the medulla of this vascular bundle before going into the xylem. So we have to talk about active transport, mineral ions, cortex, apoplast, symplast, and vacuolar pathways, the endodermis, the Casparian strip, which is found in the endodermis, the medulla, the xylem, the process of osmosis and water potential. We also need to talk about mass flow as well. And then once we've gone beyond the roots, we have to talk about how water is getting from the roots, how it's moving up the xylem, into the leaf, and then out of the stomata, and how this is creating a pull effect, which we call transpiration. So we have to talk about the properties of water and how they're dipole. And because of their dipole properties, we get adhesion and a cohesion occurring. We need to talk about not just the pull of water, but there's also a push of water coming from the roots. There's a transpiration pull. The capillary action, the narrowness of this xylem and how water can stick to the edges and move up. The tension that's created in the xylem. And then, as just mentioned a second ago, the stomata and evaporation. So, in order for water to get into the root in the first place, we need to have, well, the first thing that's created is a water potential difference. So, active transport is involved first. The soil surrounding this root is full of mineral ions. And these ions need to be actively transported in. And when they're actively transported in, the inside of this root is going to experience a low water potential. Just do that signal there. There's going to be a low water potential, or lower. And the water potential will be lower than it is outside. And if the water potential is lower than it is outside, water is going to enter by osmosis. And this low water potential, this is being kept lower and lower and lower and lower as we go further in. As those ions are being moved through the cortex all the way into the actual vascular bundle, there's this perfect gradient of the water potential getting more and more negative as you move in. So osmosis can happen very easily because of this. There's a constant gradient happening. So the way that water moves via osmosis, we have our symplast pathway and our vacuolar pathway. If you've forgotten this, watch the video from before. Because there's a low water potential here compared to outside the soil, the cells in this region are filling up with water, and that's creating a hydrostatic pressure. So there's a lot of water in this region. So as the pressure builds up more and more and more, it's going to start pushing the water away. And this type of movement of water is something we call mass flow. And this mass flow takes place in the apoplast pathway. So water's being pushed through the cell walls, or along the edges of the cell walls, all the way to the endodermis. So all this is happening in this region called the cortex. So to get from A to B, active transport had to occur of mineral ions. This lowered the water potential and therefore water entered. We've got a steady gradient of water potential getting lower and lower and lower as we get to the center of the cortex, and therefore water keeps moving by osmosis. And because of the high amount of water in this region, water's being pushed away, causing mass flow, and there's our 3 water pathways. Now we get to this region here, C, the Casparian, the endodermis. And this is a layer of cells which contain something quite unique called the Casparian strip. And it's a waterproof layer that's running through the whole way. And it's running through the cell walls. And what this is doing, it's preventing the apoplast pathway from continuing. Because the apoplast pathway, if you remember, is the pathway which runs through the cell walls. Suddenly now it comes in contact with this waxy layer, and it's forced inside the cells, in with the cytoplasm, and then it's the water that was moving through the apoplast pathway is now being forced into the symplast pathway. Okay, and this is important because what it's going to do, that water, it's not just water, there's lots of ions in that water traveling as well. And in particular, a really important one is nitrate. And the only way we can get nitrate into the xylem, because the nitrates are needed throughout the plants, it has to get in across the cell membranes. So it has to enter the symplast pathway. And then when it gets across this endodermis, it's now in a region called the medulla, which is just this tissue surrounding the xylem and the phloem. So we've gone from the outside, across the root hair cells, along the cortex, and then we've got to the endodermis with the Casparian strip. It's been forced, the apoplast pathway has been forced into the symplast, and now we're in the medulla, and now the water can finally get into the xylem. So osmosis, created by water potential, mass flow, this is the apoplast created by the large amount of water which has been entering in this region here as it's been coming in, as the water's been following the mineral ions which were actively transported. Next thing to talk about is the properties of water. So we say that water is a dipole molecule, and if we were to do a little image of it, that's a really bad picture, that's all right. There's our oxygen, there's our hydrogens. And again, you'd have to, I'm not going to explain this now, but the hydrogens are slightly positive and the oxygen is slightly negative. So we call this dipole. One part of it is slightly negative, one side is slightly positive. So because of that, if 2 neighbouring water molecules are together, the hydrogens again, the slightly positive and the slightly negative regions of the molecule are going to interact and form an attraction. So the oxygen, the slightly negative oxygen, the slightly positive hydrogen are forming a weak hydrogen bonds that's holding them together. And this is what's creating cohesion. So water molecules can stick together. And then we've got other properties of water. Because of this dipole nature, it's also forming interactions with the walls of the xylem. So they're sticking to each other, and they're sticking to the sides of the xylem walls as well. All right, so I've shown this differently now. This bottom part, we've got the root hair cell, the cortex, and endodermis. These are representing what we've just seen here. This was the cortex, the endodermis, and the outer part was the root hair cells. Root hair cells, cortex, endodermis. So water, you can see, is passing straight through the middle, which represents the symplast and vacuolar pathways. And the outer part here, let's use my arrow actually, the outer part is showing the apoplast pathway, and it's getting to the endodermis, and this orange region here represents the Casparian strip. The apoplast pathway has been forced into the symplast, and therefore it has to enter the same way across the cell membrane, and therefore bringing all the good mineral ions with it, like nitrates. Right, why is water moving up the roots, up the xylem? Well, let's focus on the first one, which we call the transpiration pool. Water is evaporating from tiny holes at the bottom of a leaf called the stomata. And you can see we've got the liquid water. When it gets to the stomata, it's vaporizing. And when it evaporates, it leaves behind an area where there's no water, and that needs to be filled by the water in this region here. So as the water moves into this gap, because the water molecules are all stuck together with the hydrogen bonds, there's a big column of water molecules all stuck together, and they're all being pulled up together as one big column. Okay, so the pull is happening because of evaporation. So you could say that evaporation is driving the process of transpiration. Evaporation is what is causing the pull of water up the xylem. And there's another feature that's causing the movement of water up the xylem, and this is root pressure. So because water keeps entering, and there's a high hydrostatic pressure of water in this region, and it's pushing water along the apoplast pathway, there's a mass flow. Because water is entering a lot in this region here, it's able to push the water up the plant as well. So both processes are happening at the same time. Okay, so there's another part of transpiration. It's known as the cohesion tension. Let's write down cohesion tension. And this is to do with how water is moving up the xylem. So the cohesion part I've talked about, the fact that the water molecules are stuck together. If you can pull one molecule from the stomata region as it vaporizes, if one gets pulled, they all get pulled because they're all stuck together. Now there's tension created in the xylem. So because water's being pulled out of the xylem into the leaf, I want you to imagine if you were to put your finger at one end of a straw and then put your mouth at the other end of the straw. If you then suck the straw, the sides of the straw get pulled in and it closes up. So that equivalent is happening in the xylem as well, and that needs to be counteracted. That tension, if lignin isn't present in the walls of the xylem, that xylem vessel would collapse on itself, and that would cause real problems. So the lignin's there to help to support the xylem, to keep it open so that water can keep moving up.